Hey everybody. Yeah, this is a really lovely workshop. It's nice to have small groups of people and people can interrupt. I interrupt a lot, so if people want to interrupt me, that's also fine. It would be very hypocritical for me not to accept that. I know that not a lot of people work on decoding in this group of people, and so my main goal here is not to tell you all about our research in decoding. It's more to set the scene for what decoding is. I will talk a little bit about that, but I kind of mainly want to give like the conceptual side of things and illustrate, why we're trying to do this, what are the big challenges, where we've got so far. So yeah, we'll come to it, but that's kind of the main goal. I wanted to kind of set the big picture scene with regard to this conference with this slide. So this is kind of a rough sketch that sometimes I like to remind myself of. So it's very, very loose. But on the x-axis here, we might have the number of physical qubits that you have in a system. This blue curve represents roughly the algorithmic capability that you can achieve with that set of qubits if you don't use fault tolerance or quantum error correction. And the point I'm trying to make here is I haven't even labeled what my unit is here, but let's say it's 1 perfect qubit worth of capability. So this is a straight line, a linear one-to-one at the start, until the noise starts affecting you. And then eventually, it doesn't really help very much to add on more qubits because you can't run bigger circuits. And so things kind of plateau and flatten off. And this is still a very interesting regime. We have seen, or at least I believe that we have seen quantum advantage be demonstrated within this regime of not yet having fault tolerance. And I think that's very interesting. But ultimately, we are going to want to do fault tolerance so that we can kind of keep going and do more. And there's kind of an immediate issue that you run into when you think about this, when you use fault tolerance, which is all very kind of clear to all of us, which is that it costs something to do fault tolerance. And just in this scale, which ignores a lot of things, even just number of physical qubits that you need to encode one logical qubit, even using all of the quantum LDPC codes and the new ideas, is still at least 10 or so. And it's going to be probably worse than that. You also have other issues when you go to fault tolerance, which is that we have the discretization of the instructions, which is something that I like to remind people who are going from NISQ to fault tolerance of a lot, because the algorithms like VQE, et cetera, they imagine that we have these arbitrary angle rotations. Those are very expensive to implement whenever you compile them down into fault tolerant discrete gates. And so you really have a lot less power when per physical qubit when you go to fault tolerance. So it's gonna take quite a long time before we achieve what you might call logical advantage as an analog to the quantum advantage, where the actual capability of our circuits using fault tolerance is better than what we can do with physical qubits. And you can ask, how long is it going to take for us to get from here, which is kind of where we are today, a bit beyond quantum advantage, to this other regime, and also how many qubits is it going to require? I think that depends a lot on the ideas that people are developing at the minute. And it's going to require many problems to be overcome in order to achieve this and actually get into this regime, which include, of course, building more qubits, but also having better codes to make use of those qubits, logical operations to perform the actual computation, architectures to plug everything together, and other pieces too. Another thing that you might say is, well, Michael, you're kind of making this up. These are all just hand-drawn lines, and that's true. But I think that if you actually include the more complicated things, it pushes this further out, not closer. What happens is, for very, very small experiments, perhaps you need small numbers of physical qubits per logical qubit because you're using low-distance codes. But as you get to larger distance codes, then the encoding rate gets worse. And also, with all of the great ideas like error mitigation and other things, you actually push this blue line up a bit, which is good, but it does push out quantum logical advantage to further and further to have higher and higher requirements. So I think it's going to be quite a big system before we really hit this, and we have to accept that, but also work hard as we are to try and get there as quickly as we possibly can. So this is a picture that I really like to kind of put different parts, different problems that we need to solve into context. This is kind of a conceptual stack of quantum computing with the most abstract things at the top. So think of this as like a research paper, maybe Shor's original paper for factoring. And then at the very bottom, it's what you actually build. And each of these layers will have some very specific kind of set of things that you're allowed. So at the top, it's math. At the bottom, it's going to be literally physical hardware and pulses and things that you can apply on that. And the kind of world that I usually live in lies, in my research, lies in these kind of three layers I'm going to briefly describe now, where we treat each physical qubit as a dot. It's kind of abstracted away. We have a graph that represents operations that you're allowed between those dots. And then quantum error correction, which is zoomed out from that layer, slightly abstractified, where we have stabilizer measurements of a code, perhaps, that we use. And then above that as well, I should say before I go on that these must be consistent, these layers. So if you have some check that you want to measure here, then you have to be able to achieve that using the physical operations at the layer below. So they have to be consistent with one another. And then the quantum error corrected code that you build will kind of induce some logical operations and allowed operations between your logical qubits and the layers above. Something that we're interested in IBM, of course, is using different codes than the surface code, which is what I just showed here. And that has implications all throughout the stack. So if you want, here's a different check that is no longer 2D nearest neighbor on a grid, which you might need to implement the kinds of codes that Eddie was talking about. And that means that you can't get away with 2D nearest neighbor C-naughts on your physical qubits. You have to be able to do something more complicated than that, long-range gates. But it also has implications up the stack for the logical operations and compiling that Eddie was talking about too. And that is, the end of the picture that I would normally describe in most of the research that I do in fault tolerance and error correction. But I'm actually going to talk about a whole other thing, which is kind of adjacent to this, which is that we need, for all of this, to have a classical support stack in order to make it all work and actually form a useful quantum computer. So what I'm going to be talking about today is the decoding part of this, and in particular decoding for quantum LDPC codes. Okay, so what is decoding? I think probably most of you know this, but just for the few who haven't heard it before, it's really just the fact that in a fault-tolerant quantum computer, measurements, operations and measurements are being made in some circuit on the hardware all the time. And the data that you receive from those measurements is used to detect and then identify errors. And the decoder is a classical algorithm that takes in that continuous stream of ones and zeros, or perhaps other side information from these measurements, and decides what went wrong. So that's the decoder. And in the rest of the talk, I'm going to kind of remind people of quantum error correction and fault tolerance, describe what the actual decoding problem is as a math problem, and then talk about real-time decoding, which is kind of the main challenge for decoding in this talk. And then I'm going to talk about some things that we need to incorporate in order to be able to actually achieve real-time decoding, or at least we think we do, which is parallel classical computation, so not using CPUs, essentially. And then I'll talk about where we've gotten so far, how fast are we, and what we still need to do. Okay, so quantum error correction, I think this will be very familiar to everybody, so I'll go really quickly through this. This is a picture of the Steen code with qubits being dots. You have X checks being stabilizers in each of these faces, and similarly you have Z checks being Z's on each of these faces. And the decoder is just the classical algorithm that identifies from the outcome of the measurements of these checks what error probably occurred. So just to kind of give an illustration of this, the decoder takes in this picture, this little triangle, and a yellow means that some error happened on the support of that stabilizer, and a gray means that it did not. There was no error, or an even number of errors happened. And you can kind of see here that from the pattern of which little face is yellow, you can identify which individual qubit error could have explained that particular pattern. So the decoder is just, in this case, the kind of lookup table, or the working it out on a piece of paper of which error happened given that pattern. Fault tolerant, so that was error correction, and that's kind of what is taught very early on. And then fault tolerance is kind of like error correction for grown-ups, or you can think of it as kind of like this slide that I borrowed from some friends, where fault tolerance is like putting out a fire, but where the fire extinguisher that you're using to do that is also itself on fire. And that, of course, causes more problems. In reality, what does this mean? We need to measure these syndromes to identify whether a face is yellow or not. But what if you just get the wrong outcome? That could also happen in your faulty hardware, and that makes the problem much more difficult. So I'm not going to go into details on this, and this is actually just a made-up circuit, so don't even really pay too much attention to it. But the point in fault tolerance is that we have ways of handling this, and in order to actually implement a logical operation, we accept that we're going to have faults in our circuits that we're actually applying, and then the effect of that is that the logical operation will be something we can correct. So one way that you can think about this, which Austin Fowler has left, so we don't need to worry about his picture right now, but it's not exactly the way that Austin was putting this forward. But one way to think about this is that you can imagine each logical operation that you would like to be able to perform. You have some circuit that is capable of performing that. They might look different. So like you might have one circuit for, say, the S gate, another circuit for the Hadamard gate, but they all come with guarantees that if some faults happen, and you can detect the effects of those faults, and then you run a decoder to figure out how to fix that. And then you can zoom out, forget that you did all of that, and just use these logical operations and plug them together. So this is kind of how we see building a large-scale quantum computer working. Okay, so what is the actual problem? It's a classical problem. What is the problem that we need to solve? Well, it's quite simple to specify, so I think it's worth just stating it. So we have a pair of matrices. We have a check matrix, which is probably very familiar to people. And then we also have an action matrix, which tells us what happens to information stored in the code. So I'll describe this in a little bit more detail in a second. And then the last object that we have in our problem statement is a vector of probabilities. So all of these things have n columns. And each of those n columns corresponds to a discrete fault event that might happen in your system. And the probability vector at the bottom just assigns a probability to that event happening. The error, so the set of all errors that can occur is then represented as a length n bit string. If there's a 1 in a particular location, that fault happened. If there's a 0, that fault did not happen. And the syndromes, so the things that you actually detect in your circuit, are represented mathematically by just acting the check matrix on that particular bit string of errors which happened, which you don't know. So E happened, you don't know what it was. Sigma is the observable that you can actually see. So the decoder, the classical algorithm, knows in advance what these matrices and probability vector is. It does not know E, but it does know sigma. So it observes sigma. That's the input to the decoder. And then based on that, it guesses a correction. So it guesses some E hat. Of course, if E hat and E are the same, then it fixes the error. But we actually have a little bit more freedom than that because of equivalence classes and quantum error correction and stabilizers, et cetera, for those who know. But the idea is that if both the syndrome and the action of E and E hat are the same, then the decoder succeeds. So that's the requirement. So this is the problem that needs to be solved. Yeah, you have a question?
Did you say why we need to model the decoder as a matrix? Like, why not do something more sophisticated?
Why not do something more sophisticated?
I don't know what that would be, of course, but.
Yeah, so I would like to come back to that in a little bit of detail, not because I have slides on it, but because I think it'll probably be a little bit easier to discuss later in the talk. But yeah, this is a model. What I just described is a model of noise in the system where every fault is a discrete event, and it is assumed to occur independently with some probability. And that is not really what the real world is like. So we will come back to that a little bit later. Okay, so I'm not going to explain this, but give me just a second. But just because this is going to be very fast. These things are basically just what I described before. So I showed the picture of this code. You just, to obtain the check matrix, each column in the example that we did before, so like this is the first column, this is the second column. Each of these z's being in a different location is a different fault. And the syndrome is represented by the entry here, the column. So this one, the top one is yellow, so it gets a 1, 0, 0. The top one is gray, so it gets a 0, 0, 1. So and so on. So you kind of just write these things down from your model. There's a graphical representation of this, which is just, you can always represent the binary matrix by a bipartite graph like this. So these are equivalent. But yeah, there's a circle node for each column and a check node for each row, and you have an edge but when there's a 1. And you can do the same thing for the circuits, where not each thing that goes wrong in the circuit has an effect that you can observe that gives you the entry in the check matrix, and also an effect on the logical information that's encoded. And I'm not going to go through an example in detail. There were some questions, so go ahead.
I guess you define decoding as trying to guess the physical error E that happened here. But I could also define a weaker notion of decoding where I just want to guess a logical flips, like x1
so that,
or x2 bar.
Yeah, so maybe it wasn't clear the way I described it, but the latter is what we're doing. So if we wanted the E hat to be equal to E, then we would be doing what you described. We'd be identifying what happened. But we don't actually care. So as long as E hat has the same image under both the check matrix, so it has the same syndrome, and the action matrix, so it has the same logical action, then we accept it. And that means, for example, they could differ by a stabilizer.
Right, but do you actually need to get a physical error like output from the decoder, or do you just want the vectors of logical flips, for example?
It depends on what exactly you're planning to do. Yeah, we can talk about that. There are some relaxed notions, but in my opinion, ultimately, it always implicitly boils down to deciding an actual error, even if you're not doing it, because probably what you're in fact doing is storing some extra basis information and computing the flip with respect to that. But anyway, we can discuss that after. Okay. So, any other questions before we keep going, or yeah, go ahead.
Why is A linear?
Why is A linear? So in this particular noise model, which I'm assuming here, the effect of all of the noise is linear because the noise in this noise model is stochastic Pauli operators that act on the circuit. And the effect of a stochastic, the effect of any Pauli operator acting on, a Clifford circuit is linear. Is that sufficient for your?
Should I be thinking about A as acting on the physical qubits then, or okay.
Well, yeah. So A acts on the set of faults, and so does H.
Sorry, no, I mean the left dimension, the low dimension.
So each row corresponds to each row of H corresponds to a detector. Each row of A corresponds to a generator of the logical space. So if you have in our case, we have 12 logical qubits in a particular code block, there will be 24 rows of A. One for all of the, one choice is one for each logical X operator and one for each logical Z operator. Does that make sense?
So should I be thinking about if you take AE and there's like a 1 in the column, that you flipped that logical operator?
You applied either a logical X or a logical Z, depending on what row it was, yeah.
But wouldn't that need to be a polynomial in weight D, right? Because you need D, for example, let's say you needed D correlated flips for
So if there was no syndrome, so if you had a bit string which H acted on and gave you 0, and A acted on and gave you something non-zero, it has to have weight at least D, because that's a logical operator. If you don't satisfy the syndrome equation, you do not have that guarantee. Yeah. Okay. Okay. So the point that I want to make here is, we had this toy example of a very small check matrix, but in practice, these decoding problems are really big, and that's kind of the point. This is a tiny problem. This is a distance 3 surface code, and there's a lot of different faults that can occur, and a lot of detectors that you need just for a really small system like this. And this is, we can't draw the systems that we actually are interested in. So this is kind of about the size of the system that Eddie was talking about in the previous talk. To decode this, we need a graph with roughly 100,000 nodes and about 1 million edges. And that's not even for the biggest examples that we might want to decode. So these are quite large problems that need to be solved. Yeah.
Is a 12-cycle window life sufficient for gross coded Eddie of what we had previously?
A 12-cycle window is certainly sufficient. It's probably overkill.
Okay.
But
What was the distance of that gross?
12.
Okay, that's probably fine. Yeah.
Okay, so this is a big problem, as I mentioned, but we also have to do it fast. So why do we have to do it fast? So the quantum error correction cycle for superconducting qubits, which is not all hardware types run as quickly as this, but superconducting qubits, one cycle lasts about a microsecond, and as was just discussed, we probably need on the order of 10 of those in one logical operation. And this is kind of back of the envelope here anyway, so I'm going to be a little loosey-goosey, but that means that we need roughly 10 microseconds to solve a decoding problem if we're going to be ready for the next logical operation decoding problem once it's happened. So the point is, if you, roughly speaking, logical operation is happening, it takes 10 microseconds. We start decoding that as soon as it's done, and then we're going to have another one right after, so we want to be ready for it. So that's kind of roughly the timescale that we need to decode in. But there's some other constraints that we want. We also want our decoder to be good, so we want it to be accurate enough to make the logical error rate low so that our quantum computer works. And we also want it to handle a very general check matrix H. So this is something that maybe I want to highlight a little bit. If you only wanted to deal with surface codes, this top red bullet point would not be true. There's a lot of structure for surface code decoding problems, and that actually allows you to use some very nice special decoders. When you leave surface code land and you look at LDPC codes or other codes, then the decoding problem becomes much more difficult, to the extent that it's probably reasonable to just assume almost nothing about the decoding problem and just assume you have a sparse check matrix. Yeah.
Can you just design the decoder specifically for the LDPC code that you're using?
Can you design the decoder specifically for the LDPC code that you're using? Yes, you should use all of the information that you can figure out a way to. The kinds of LDPC codes and logical operations that have been implemented in these LDPC codes do not have enough structure that people have been able to really exploit that to a high level.
Are we talking about BB code, for example? Or?
Yeah, for example, the bivariate bicycle code. But remember, it's the bivariate bicycle code with implemented in a circuit with lots of different noise mechanisms and with an ancilla system to implement a logical operation, like Eddie was saying, coupling other bivariate bicycle codes together, or a magic state factory. So it becomes quickly a very complicated problem. And so a reasonable approach is to try and design a decoder that can handle a very general problem. But perhaps we can take advantage of structure. Okay, so I claimed that we want to solve the decoding problem roughly as quickly as these logical operations are being generated. And that's maybe fairly intuitive, but I want to just talk it through because I think it's an important motivator. So this is a very simple picture of how a logical computation might proceed in practice. The blue is a logical operation, and the gray is an idle operation that I fill in, and I'm going to fill this in only because I need to wait before starting my next logical operation to decode. I'll describe that in a second. So time is going left to right in this picture. Oh, that's very strange. Time is going left to right in this picture, and at this point, this first logical operation is finished, and it's possible that I need to know information about that logical operation in order to decide which logical operation to apply next. And because of that, I need to actually decode it before I move on. So my decoder starts immediately after this logical operation is finished, and then if it takes some time t decode, then I have to wait that amount of time and idle in between before I go on to the next one. And something that's maybe somewhat annoying about error correction is that we have to then decode the waiting time as well. So that while we're waiting, we're just doing error correction, not doing any logic, but we're still generating syndromes, creating and identifying errors, so we have to code that too. And that's fine because I can just do that after I start doing my next logical operation, provided that this decoding time is faster than the generation time. So we have a slowdown based on this latency of the decoder, but it's kind of small and handleable here. However, if you have a decoder time which is longer than the generation time, then you can probably kind of see that a big problem arises, which is you start decoding this logical operation as soon as it's done, but then while you're waiting, you have all of these idle cycles that you put in here, each of which need to be decoded, and that takes a long time to decode, and so it increases exponentially with the number of logical operations, how long you have to wait just to handle the backlog of decoding. So this is called the backlog problem, first kind of pointed out by Barbara Terhal. And this is obviously a problem you want to avoid. One way to handle this problem, which I think is kind of in some regimes a reasonable solution, is you exploit a property in quantum error correction, luckily, which is that most codes can, but not all, you can independently decode this idle from the first idle. So these two decoding problems can be done in parallel, which means you can just use an extra decoder for this. This is not actually always true, but for most quantum error correcting codes and decoding problems, you don't need to know the decoding outcome of one before you start decoding, before you start work on the next. Yeah, go ahead.
Is this ever true for qubits that are, like you have two qubits stored in the same block, like a 422 code? Is it ever possible to decode one of the two qubits in a 422 block without decoding the other, or is it always in separate, like quantum error correction blocks that this property might apply?
No, it's the same block. So all I'm saying is, like, suppose you have, say, the surface code. You're decoding the surface code for, let's say, it's distance d, and you're going to run 2D idle cycles. I'm saying that you can decode the first D cycles and the second D cycles separately and then plug them together. Roughly, I mean, you actually need an overlap regime for people who know a lot about decoding, but what is not the case is that you don't need to know what the outcome of the decoding was for the first D as an input to the decoding problem for the second. And that can be the case. For example, with single-shot codes, then that is actually something you need to do, which maybe I'm getting into the weeds here. So there are scenarios where this doesn't work. But it also costs extra decoders. And decoders are, decoders are quite expensive to actually put and involve wires going to and from the hardware. And having multiple decoders is something that would be very good to avoid. So this is kind of one way that you could handle this, but it's not the way that I'm looking at handling it. Okay, so how do we build decoders that are fast enough? Well, one way that you can think about doing this is to use parallel classical computing rather than the kind of normal CPU type of algorithms and implementations that probably most of us are more familiar with. So just as a very high-level sketch here, I'm sure there are people in the room that know more about all of these than I do, but you can kind of class the different, most commonly known types of classical computations into these 4 kinds of buckets. CPUs is what we're most familiar with. They're kind of centralized, very quite large and powerful and general purpose processing units. And then GPUs are much more widely known today than they maybe were a few years ago, and they are more fine-grained, but they still have fairly general purpose, specific small numbers, relatively small numbers of blocks that are used for specific computations. FPGAs are much more fine-grained than that. They're really kind of millions of very, very tiny pieces that you can program to a much lower level. And you can kind of think of these as you have access to bits laid out in a grid to some extent with some additional properties. And then an ASIC is really kind of like you just build your own computer. You kind of, nothing is designed there. It's very expensive to kind of think about ASICs and algorithms written in terms of ASICs. And what I would like to focus on here is this regime here, because you have quite a lot of control over the parallelism, which in the algorithms I'm going to describe, we would like to have. But it's much more easy to program than, say, an ASIC, which is more general. Sorry, question?
Can I just like very easily, naively understand you trying to build like a Boolean version of GPU?
Well, it depends. I mean, let's discuss it afterwards. Yeah, let's discuss after. Okay, so I'm not going to actually talk about this slide. I just want to flash it. There are very clever ways that FPGAs are built that allow this kind of parallelism to be exploited. And I'm not going to go into the details of that. I'm actually going to tell you instead about a mathematical abstraction that I think is very useful, that allows us to kind of reason about how algorithms work in FPGA land. And this is really just a network or a graphical model of an algorithm that is it's basically like pseudocode for FPGAs. And the idea is that you have nodes, and the nodes can store a very small amount of information, say one bit or 2 bits, something like that. And you have edges between nodes. And the edges can transfer very small amounts of information, say 1 or 2 bits, or potentially also a control signal to tell the node to do something differently than it might otherwise have done. And the algorithm proceeds as just a sequence of iterations where every node takes in a bit on the incoming edge. It combines that bit with its memory, applies some very, very small logic operation on it, like a 2x2 matrix or something like that, and then spits out the outgoing edges, the information that was computed, and changes its stored piece of memory. And it does that over and over again, and you can implement an algorithm in this way. It's kind of like cellular automaton, if people have thought about that picture. There are different pictures that you can imagine drawing, like different graphs, for example. I've drawn up here a 2D grid. That is one type of graph. This picture with the 2D grid in this computational model that I've described is known as a systolic array. And this is kind of the pinnacle of what you might try and do really fast in an FPGA. Everything is 2D local, and if you can design an algorithm that looks like this, then you can it's really native for an FPGA. FPGAs are actually able to do a lot more than this, but this is kind of the thing that they are best at. And I'm not going to talk about that in too much more detail, but if you have long-range connections, you can still implement that in an FPGA, but it can slow things down, and so that's something to consider. Also, global control will slow things down. In a systolic array, you have no global control. Okay, so what kinds of decoders could benefit from this? And I don't have a lot of time, and it's also kind of impossible to talk through all of the different classes of decoding algorithms that people have thought about for quantum LDPC codes. But I'll kind of just name them, and maybe you can kind of imagine what kinds of things they might be like. So the decoders fit, to my knowledge, into these classes. So we have basically mapping the math problem I described earlier to a SAT problem, and so using just off-the-wall SAT solvers for that. You have kind of search-based methods. So decision tree decoding or tesseract are examples of that. You have neural net decoders. There are message passing decoders, and then also order statistics decoders, which maybe it's not too obvious what that means. I won't go into it. And also clustering decoders, which kind of take advantage of the graph structure that I addressed earlier, but I also will not go into too much detail. So in this picture where I'm focusing on FPGAs, I would say that these decoders are kind of, to a large extent, ignorable. The first set, as far as what we know so far, they're just too slow. They can be optimal. So both SAT solvers and search-based decoders can be optimal, but they're just too slow for real-time decoding, unless there's some big breakthroughs there. So I would be hopeful for that, but it doesn't seem clear that that's going to happen. Neural nets, I think, are actually more plausibly useful for real-time decoding, but if you were going to do that, I don't think you would use FPGAs. You'd probably use GPUs, so I'm kind of going to ignore that for that reason. Message passing, okay, I'll skip that. Message passing decoders and order statistics decoders and clustering decoders are what I'm mainly going to focus on. Don't worry, I only have a few minutes, so I'm going to kind of give some high-level info. But the reason for this, message passing decoders are really parallel, and so seem very kind of obviously implementable in an FPGA. The reason to focus on these other decoders is actually because both of them have at their core Gaussian elimination as the kind of main repeatedly called subroutine, which makes most people not think of them as fast decoders, because Gaussian elimination is a cubic time algorithm on a non-parallel computer. But Gaussian elimination is linear time in parallel, if you implement it in parallel. And so it kind of opens up the possibility that these decoders could be useful. Yeah, go ahead.
And it's also a Gaussian elimination on a binary matrix.
Yes.
Right, so that's significantly better as well.
Right. Okay, so I will just show some pictures to kind of illustrate this. This is a decoding graph. It's a decoding graph for the color code for people who like codes. But the point here is if you want to implement a message passing algorithm on this kind of a code, it's really very directly related to the picture that I showed earlier. You just assign, to each node, so each of the fault nodes gets a specific small little function, which basically computes an update rule that it passes messages to its nearest neighbors, and also stores a Bayesian update of its inferred probability of a fault having occurred there. And then the check nodes get another function which computes the messages that it has to send. And you just run this repeatedly over rounds until the Bayesian update produces a correction which is consistent with the syndrome, and then you stop. And each of those rounds is in a CPU will take you a number of nodes time to run, so linear time, but on a parallel implementation on an FPGA, it will be order 1 time, so it's very fast. This is essentially the approach that we are focusing on in IBM. I'll kind of show a figure to explain why. But there are some issues with this kind of algorithm, and perhaps you've heard of this before, but the issue with message passing algorithms is that if you apply them on graphs with loops, you can end up getting little messages that kind of reinforce themselves in the loops and start to do crazy things. So they start to oscillate. The belief, just this figure I think is helpful, the belief that an error happened at a particular node can go up and then go down again because messages are coming around the loop and kind of reinforcing and causing them to change their mind back and forth. And so the algorithm that we use with message passing called relay tries to address this. And the first way it tries to address this is just as any physicist would, you introduce damping to the system to stop the oscillation. However, damping to stop the oscillation can damp your belief of an error happening instead of being 0 or 1 to just, I don't know, which is the kind of middle value here. And so in order to avoid that, this can occur because you have symmetries in the system. So whenever you damp the messages, then it converges to uncertainty. And so you can introduce disorder, and that kind of breaks a lot of these symmetries. And it seems like a very obvious idea, and there's kind of an art to coming up with these message passing algorithms. Relay seems, at least from the people who talk to me in different groups, still to be kind of the best algorithm for handling LDPC decoding. And yeah, it works pretty well.
Just a question.
Yeah, go ahead.
You said disorder. What kind of disorder?
So the memory that we introduce, we disorder the strength of the memory locally. Yeah. Okay, so that's one thing. Gaussian elimination. I'm not going to explain how Gaussian elimination works in linear time. We actually had to come up with a new parallel decoder because the previously known systolic decoders, or the previously known systolic algorithms for Gaussian elimination all assumed full rank. So this was a lot more complicated than I was expecting it to be, but I learned a lot while doing it. All I'm going to show here is just the kind of algorithm that you can run in a systolic array. Here you have 2 bit strings, this one, bit string B and bit string A, and there's a simple rule at each node, and a message can be passed by each node. And you flow the input bit string in through the array at an angle so that it's computed, and whenever it's computed, it sends a message just in time for the next element to know what it's supposed to do based on whether it's an elimination or not an elimination. And you can just flow it through the array like this. And of course, instead of just having 2 bit strings, we have a full matrix. But this is essentially how Gaussian elimination works. It's very beautiful, and it's, yeah, these algorithms are very cool. So what happens when you look at everything all together? What do these plots show? Well, focus on the left one. It's just 2 different codes. So if you focus on this one, on the x-axis, we give a budget of FPGA cycles that we allow the decoder to run. If it has not yet terminated, we say it's failed. And then we compute the logical error rate that has been achieved at that time. So some will terminate before that budget is up. And if it's worked, we say it's succeeded. If it fails, we say it fails. If it has not yet terminated, we say it fails. So this kind of gives you an idea then of how accurate the decoder is with different runtimes. How fast is the decoder that we need? It's this line, and this is the curve that we get for relay. So it's very good compared to the other decoders, but we still have a problem where sometimes the decoder is too slow, and we miss out on all of this accuracy if we cut it off at this time. So I'm out of time. There's a couple more slides that I won't go through, which talks about how we handle those cases, how we handle the fact that no decoder really finishes in a particular time. It kind of depends on the decoding problem, and how you handle a variable latency in a decoder. But I would say that's kind of where we are. We would like it to be faster. We would like the worst case to be faster. If we don't get a faster worst case, we can handle it, but it makes inconvenience for the quantum computer. So, okay, I'll finish. It's the end of the day, so I think it's, yeah, there we go. Okay, so thanks a lot.